Happy birthday. So first speaker doesn't need an introduction. He's the champion, as has already been announced, with a score of 17. What was it? Please take it away.
All right. Well, it's wonderful to be here for this very, very nice occasion celebrating Jeff. The title of my talk is Partita for Jeff, because my talk splits apart into several natural parts. So we begin with prelude. I first met Jeff in Jadwin Hall in 1982. And then I left. I was a senior at Princeton, and I left Princeton. But amazingly, we continued to correspond by P.
That doesn't use P out of numbers.
No. P is not a prime. And yeah, I have some of those letters. Our first paper was in 1987. It was a very fun paper with Coulomb, where we used quasi-crystals to compactify string theory. And already there you could start to see some of the themes of my later work with Jeff, where we used beautiful lattices with interesting number theoretic properties. So it's interesting that already in that first paper there's some aspects of that. You all know that Jeff is one of the wittiest and funniest physicists in the field. And aside from the great science, one of the joys of collaborating with Jeff is that we start to get into some really great email banter. And I'll tell you just about two examples of that.
Wait, how come I never got it?
So this was sent to my next station at Yale in October 1994. I mean, what more is there to say? And the other one was once in 1998. I told Jeff that I had the evening before I had danced the Macarena for the one and only time in my life. And of course that led to some banter, and the Macarena became Maldacena. And I believe, I do not know, I never checked this with Jeff, but I believe this might have had something to do with Jeff's career as a singer-songwriter. So this is from the New York Times, 22nd, 1998, and the rest of the lyrics are in the New York Times article, and they're very brilliant. I definitely recommend it. Jeff also has a razor sharp wit, and I've been on the sharp edge multiple times. But I'll tell you about one, just one example of that. It was the summer of 1986 at the Aspen Center for Physics. And I was really proud of myself because I had just written a paper where I was the first person to write down the genus 2 amplitude of the closed bosonic string. So I learned about the Siegel cusp form weight 10, and I realized immediately that's exactly what we need. So I was very, very proud of myself. Now you have to understand for this story that in those days, the way we would learn about scientific advances in the Soviet Union was that a Western scientist would go visit Moscow and Leningrad and talk to the physicists at Moscow and Leningrad, and then smuggle out a bunch of scientific documents. They might look like this. I particularly like the one on the right. It says, "Dear Dr. Moore, my name is Maxim Kontsevich. I am from Moscow. Maybe you remember me." Anyway, so this is the kind, and then the Western scientists would come back to the West and photocopy this, and it would be distributed among scientists in the West. So anyway, back to Aspen, summer of 1986. I was very proud of myself with the genus 2 amplitude, and John Schwartz shows up, fresh from a trip to the Soviet Union. And he has a suitcase full of these kinds of documents, and he opens the suitcase, and he pulls one out, and it's a paper from the physicists in Moscow, Morozov and Vadim Konishnik, and it has the genus 2 amplitude. It's very crestfallen. Then John pulls out another paper. It's the genus 3 amplitude. And then John pulls out another paper. It has a conjecture for the genus 4 amplitude. And Jeff's comment on the situation was that I had genus envy. I'll never forget. So another shared interest of mine with Jeff is that we're both very passionate about classical solo piano. In fact, we put together the piano at the Aspen Center for Physics together. It's a very long and complicated process, and there was only one mistake. It was Jeff's. At the very end, he glued the external power cord to the back end of the back panel instead of the internal end of the back panel. But no harm done. You see, it looks beautiful. It plays beautifully. And this is a nice occasion then to give Jeff his birthday present. Oh. And dear Jeff, I hope someday you will enjoy.
Well, thank you very much.
So now for the scientific part of the talk. So it's the first part will be a sort of leisurely a la mode. The topic will be moonshine phenomena, supersymmetry, and quantum codes. Now, Brandon touched on many of these aspects yesterday in his very beautiful talk, but I'll elaborate. So let me begin with some philosophy. So physicists can be divided into two types. So type 1 believes that our world is a random choice drawn from some huge ensemble, rather like this, one of these jelly beans. But type 2 believes that
type 2B.
You'll anticipate. Type 2 believes that the fundamental laws of nature are based on some beautiful, exceptional mathematical structure. I believe Jeff is type 2. Even though he is co-inventor of the heterotic string. And I believe this partly because of his enduring interest in the relation of 2D conformal field theory to finite group theory. So as Brandon was reminding us yesterday, one of the great achievements of 20th century mathematics is the classification of finite simple groups. And that's a relevant thing if you're interested in group theory, because there's a theorem that says all finite groups can be broken down in a very precise way in terms of finite simple groups. So what are they? So there's the cyclic groups of prime order, and here P is a prime, and the alternating groups, and the Lie groups over finite fields. And then there are the 26 oddballs, of which the largest is the monster. And just to illustrate that this is a continuing interest, an enduring interest of Jeff's, this is a recent paper, in fact, the paper that Brandon talked about. And this is a figure from Jeff's paper. And it's much better than the analogous Wikipedia figure. It's much better. So the connection to conformal field theory goes through moonshine. So let me remind you that in the late 70s, Mackay and Conway Norton made some remarkable observations. Mackay started with the famous modular J function and looked at its Fourier expansion and compared it to the list of dimensions of the 194 irreducible representations of the monster group. So I've listed a few of them here. There are 194 of them. And so you can try and compare the JNs to the RNs. And we start with noticing that J minus 1 is R1. R1 is the dimension of the trivial representation. That's 1. That's not very exciting. That's a normalization. Once we've normalized it, then J1 is R1 plus R2. And J2 is R1 plus R2 plus R3. And what is J3? Nobody fell for it. Physicist induction fails. But nevertheless, it's a simple linear combination. And now let's say, of course, there are infinitely many JNs and 194 RIs. So there are many ways of doing this. So let's say a way of writing Jn as a positive linear combination of the Rj's for all n is, I'll say, a solution of the sum dimension game. And there are infinitely many solutions. You could always make up any deficit with just copies of the trivial representation. So which of these, if any, are interesting? Well, we notice that every solution defines an infinite dimensional z-graded representation of the monster group, like that, and therefore we can calculate characters. And now we could say a solution of the sum dimension game is modular if the characters for every group element in the monster is a modular function in an appropriate modular group. And the amazing fact of Monstrous Moonshine is that there's a unique modular solution of the sum dimension game. And moreover, these characters have very remarkable properties, such as G0 properties. I learned of the explanation of some of these facts by using rational conformal field theory from a talk that Jeff gave at a Santa Barbara workshop in the summer of 1985, where he explained the work of Frenkel-Lepowski-Merman in very simple physical terms. And their papers are not easy to read, but this Jeff's article in this volume here really was an eye-opener. And then a few years later, Lance and Jeff and Paul wrote a very beautiful paper going further with that idea, pointing out that there should be also superconformal symmetry in what they called the monster module. That's this conformal field theory. And certainly this paper has one of the best titles in all of scientific literature. I'm sure you'll agree. So this is a brilliant paper, but there are two problems. The first is that representing...
It's not Lance and me.
The first is that in representing the standard good old Heisenberg algebra in terms of the position basis, they wrote this. I mean, really, guys? The second problem is a little more substantive. They didn't actually write the supercurrent. And it turns out, later we realized that writing the supercurrent is very non-trivial, not easy at all. So today I'm going to fill in the gap. And it's very recent work with student Ranveer Singh, and it makes heavy use of ideas from my most recent paper with Jeff from 2 years ago. And so I'm going to go explain some of that paper from 2 years ago. Now, I should say that I sent a draft to Theo Johnson-Fried, who's an expert on these kinds of things. And I suddenly got back something like 4 emails, which are really, really long. And I checked quickly through them to check that he isn't saying, oh, you're wrong, and for this reason. But I mean,
I just got an email from him saying there's actually a problem.
2 problems. So, maybe what we're doing is too naive, but Theo didn't say it was wrong. And so I'm going to tell you what I think is the solution of this. Anyway, let me tell you about the paper from 2 years ago with Jeff. So the background for that paper is the new moonshine that Brandon mentioned. So that started with Oguchi, Oguri, and Tachikawa in 2010, where they noticed phenomena analogous to Mackay and Conway-Norton, but now relating the K3 elliptic genus to the Mathieu group M24. And then shortly thereafter, that was generalized very beautifully by Cheng, Duncan, and Jeff in this topic of umbral moonshine. And we heard from Brandon that there's also 10 umbral moonshine. And it has to be said that the new moonshine remains unexplained. There's no known analog of the Frenkel-Lepowski-Merman construction explaining umbral moonshine, in spite of 12 years of intense effort by a small but devoted community of physicists and mathematicians. So it's clear that we do not understand something about the symmetries of 2D CFT, which might be important or might not be important. We won't really know until we get to the bottom of this. So Jeff and I have made several attempts to explain this. And in the course of one of those attempts, we discovered a curious relation between supercurrents and certain superconformal 2D field theories and quantum error correcting code. So I'm going to tell you a little bit about that. That's the paper. And the paper starts with a remarkable observation of Gabriel, Taormina, Volpato, and Vedland, where they point out that a supersymmetric sigma model for a very special K3 surface is isomorphic to the product of 6 copies of the bosonic level 1 SU2 WZW model. So it must be possible to write the holomorphic spin 3/2 supercurrent in the product of 6 WZW models, level 1. Now I remind you that a supercurrent is characterized by this very simple operator product expansion. So what are the dimension 3/2 fields we have? Well, the SU2 level 1 model is famously the periodic boson at R equals 1. And in that theory, there's a chiral vertex operator that looks like this, which transforms as a SU2 doublet. So I want you to think of this as a qubit, okay? And it has conformal dimension 1/4. So if I have 6 copies of the WZW model, then I can just take the tensor product of these, where these epsilons 1 through 6 are plus or minus 1. So that gives me 2 to the 6 vertex operators with conformal dimension 1/4 times 6 is 3/2. And so that's the right conformal dimension. So, okay, so we have these fields and they span a 2 to the 6 dimensional vector space of holomorphic 3/2 operators. So let's identify this space with the space of states in a system of 6 qubits. So for any state in the system of 6 qubits, there's a vertex operator. If the state is called S, I'll write it VS. And so which one is going to be the supercurrent? There's a 2 to the 6 dimensional vector space. So we look at the OPEs of 2 of these guys with each other, and the first 2 terms we like, and the second 2 terms we don't like. The capital JAs are generators of an affine Lie algebra, that's not important. The capital sigma A's and the sigma AB's, these are Pauli operators. So they generate 1 and 2 qubit errors. And I want you to think of them that way. This is what we want, this is what we got. So we got to put these terms here to 0, okay? So what Jeff and I did is we looked at the n equals 1 generator. Up to global symmetry, there's only 1. And using results of GTVW, it's the state V psi for a very special state, psi, in the system of 6 qubits, which is this mess, where the notation here is that square bracket 1, 3, 5 means that qubits 1, 3, and 5 are in spin down, and qubits 2, 4, and 6 are in spin up. So you have to take this linear combination. And GTVW obtained that by taking the obvious supercurrents for the K3 sigma model and then doing a bosonization and then refermionization and a rebosonization. It was very tedious. It's amazing they got it absolutely right. And we looked at this and we asked ourselves, is there a code that governs this quantum state? And the answer is yes, it's something called the hexacode. So I'll tell you just a little bit about the hexacode, not too much. So the hexacode is based on the field F4. So for every prime power, there's a finite field. 4 is a prime power. So there's a field with 4 elements. So it has a very definite addition law and a multiplication law. And we can then think about codes over F4. And we all know of a code over F4. It's in your DNA. Okay, but our code is much more modest. It's a 3-dimensional subspace of the 6-dimensional vector space over this field F4. Call it Leech. That's the hexacode. So I'm not going to define it, but I'll give you the very important property that it satisfies in just a slide or 2. Now this field F4 is closely related to the quaternion group. The quaternion group is a group of 8 elements in SU2, which you can think of as the special unitary bit flip and phase flip errors. Now, for every element of F4, you can associate a Pauli operator, h of x, in such a way that if you multiply 2 Pauli operators, that's the Pauli operator for the sum of x and y in the field F4. But you could do that up to a sign. So for example, here's an association of elements of F4, 0, 1, omega, omega bar, 2 Pauli operators, and they satisfy this identity, but you can't get rid of the sign, no matter how hard you try. So now, if we have a vector space of dimension 6 over F4, then if we have a vector in that vector space, I'll call it a word in these letters from F4, we can define a corresponding Pauli operator on the system of 6 qubits. And again, you can multiply these Pauli operators, and you get the Pauli operator for the sum of the code words. And again, there's a sign that you cannot remove. But on the hexacode, this might even define the hexacode, I don't know, but it's a fact about the hexacode. On the hexacode, that sign goes away. Which means that if I sum the Pauli operators over the hexacode, I have a well-defined operator, which is a projection operator. Because you imagine multiplying these and using that law, that the product of H of W1, W2 is H of W1 plus W2. It's not hard to show that this projection operator has rank 1, and lo and behold, our special supersymmetry state is in the image. Yes?
Is the green equation supposed to be read as a stabilizer condition in the error correcting code, that all of the ones have weight 1 when you act by the code?
You might be able to write this as a stabilizer code, but I'm not sure that I would interpret this as a stabilizer condition. Well, I guess, no, I take it back. I think you're right. Yeah, because that's the group. That's the abelian group. Yeah, I agree with you. Yeah, yeah, that's a stabilizer condition. Yep, question.
Sorry, it went super fast. I probably saw it wrong, but the numbers looked a bit like the numbers that appear in the holomorphic 3 form and the symplectic form on a Calabi-Yau when you wrote down.
Which numbers?
The numbers of that define the state that appeared in
Define psi.
defined psi.
But there were six qubits in each one. It was just an abbreviated
But-
notation.
You mean this
Five,
these
2, 4,
numbers?
5.
I'm not aware of any relation to calibrated geometry.
So they look like the ones with 2 numbers look like symplectic form. The one with 4 looks like omega wedge omega. The one with 6 looks like omega.
Well,
cube.
that's an interesting observation.
And the other ones look like the holomorphic.
Yeah, I
3
got the idea.
Yeah.
I got the idea. But I don't know if it's a correct idea.
There's a problem with this slide. You're missing a left bracket on 2, 3, 5.
And also on 1, 2, 5, 6.
Okay, Lance, you got me back.
That's worse than a minus sign.
So is the hexacode all the non-zero terms in that? So there are like 16 elements of the hexacode or something?
The hexacode is like a double cover of that. I think if we count, there's 16.
Yeah.
Upstairs, yeah. The hexacode is in F4, there's like a double cover, and then, yeah, I think there's 16 there. Yeah, that's right. So what happens is if you sum these Pauli operators over the hexacode, then that projects onto that state. Okay, and now with that observation, we can understand conceptually why V psi is a supersymmetry current. Because, okay, here's the OPE for the general state in the 6-qubit system. And I remind you that the sigma A's and the sigma AB's generate 1 and 2 qubit errors. So what we want to kill the terms we don't like is this, but that's exactly because this psi is in a quantum error, actually precisely, error detecting code, and that's enough to show this orthogonality relation. The qubit errors take us from that code subspace to an orthogonal space. And that's why these terms vanish, and that gives us the supersymmetry current. So that's, to me, was a very novel way of looking at generating superconformal symmetry from quantum error correcting codes. And then Jeff and I showed that the same thing happens in Conway group moonshine, where the target space is the Cartan torus of E8 with a special B field. Now that's equivalent to 24 Majorana fermions. So the dimension 3/2 operators are associated with spinors of spin 24, and the general spinor gives you this OPE, so we don't like these terms. But again, if you sum gamma matrices over a code related to an error correcting code related to the Golay code, you get a rank 1 projection operator, and the spinor in the image of that rank 1 projection operator is a very special spinor discovered by John Duncan with remarkable properties, and among other things, that spinor gives us the superconformal current.
Greg?
Yes?
Frequently, these error correcting codes are only good for, say 1 qubit.
Yeah.
And what are the conditions that tell you that the subspace is orthogonal for all of these higher order terms?
So it's the properties of the Golay code, it's the Hamming distance in the Golay code.
I mean, you don't need infinitely higher order terms, you just need the singular
Yeah,
terms
you
to
just
compute
need
the
these two terms,
OPE. So once the singular terms satisfy, you've got the right OPE and you've got the right commutation relations.
So it's that the Hamming code, the Hamming distance in the Golay code is high.
So does
Yeah.
the K3 sigma model have an n=4 supersymmetry?
So we're, first of all, yeah. So we're just looking at the n=1 symmetry, and so up to R symmetry, there's a unique one. There is actually a code that's governing the n=4 generators.
Okay.
Yeah, that's another story, but yeah. So now we're going to use these ideas from my work with Jeff to fill in the old gap in the Beauty and the Beast paper. So let me remind you what Lance and Jeff and Paul said in their paper, the RCFT approach to Frankel-Lapowski-Mermin. So for the original Monstrous Moonshine story, you take 24 free chiral bosons with target space, the Leech torus. And so lambda is the Leech lattice, and in modern terms, we're looking at a D25 brane. And moreover, the target space torus is a very special B field. So in the closed string sector, we have a B field. They describe the B field very precisely. Now they take the Z2 orbifold of that. Now, what does that mean? You gauge the global symmetry, X goes to minus X. And how do you do that? You look up the papers of Dixon, Harvey, Vafa, and Witten, the foundational papers on orbifolds. And one thing they pointed out in modern language is that when you gauge a symmetry on the spatial manifold, you have to consider all the possible gauge bundles. And there's a non-trivial Z2 principal bundle over the circle. That's called the twisted sector. And so there are twist fields. On a 24-dimensional torus, there's a 2 to the 24-dimensional space of symmetric twist fields. They're labeled by 2 torsion points in the Leech torus, thought of as an abelian group, or half lattice points, all sorts of ways of thinking of it. It's very convenient for what I'm going to say to think of T2 of lambda as lambda mod 2 lambda. Now we're interested in that D25 brane, so we're interested in the chiral twist fields, which are much more subtle. They span a square root of the space of non-chiral twist fields, a 2 to the 12th dimensional vector space S, and I'll now spend 2 slides explaining what that space is. So the orbifolding breaks the translation symmetry on the torus down to order 2 points. Translation by order 2 points on the torus. That's our 2 of lambda. The B field defines a symplectic form on that 2 torus. That's the B field that they described. And when you implement the translations by those order 2 points on the Hilbert space of the theory, you get a central extension. You can't actually implement the abelian group of translations by two torsion points. So you get what in condensed matter physics would be called a magnetic translation group. So there's a sign in there, which you can't get rid of by redefinitions because it satisfies that identity. That's actually an early example of non-commutative geometry of D branes with a B field, which, 10 years later became a very, very popular subject. So these translation operators on the Hilbert space generate what's called a discrete Heisenberg group. And that Heisenberg group has a unique irrep, yes.
Finish the sentence.
Yeah, I just finished it. The Heisenberg group has a unique irreducible representation.
I'm reading after the Coulomb, but are these translations, the 2 operators don't commute, are these coordinates or momenta?
Hard to say, we're talking about the chiral theory. Self-dual.
You should probably think of them as a combination of momentum.
Yeah, I mean, it's a self-dual field.
Okay, thank you.
I think the answer is neither, because it's a self-dual field. Okay, so this Heisenberg group, well, you can construct it very explicitly using products of gamma matrices, and in that way of interpretation, this S is just a spinor representation. So what I'm saying is for every spinor in the spinor representation of this Heisenberg group, we have a dimension 3/2 primary field, and Jeff and I speculated that once again, supercurrent would be determined by a special spinor determined by a code. But we ran into a problem. Now we needed to know about the OPE of bosonic twist fields, which is much more challenging, but several people in the room here rose to the challenge. So there's a foundational paper of Dixon, Friedan, Martinick, and Schenker that started to lay out that theory, and then it was extended by a beautiful paper of Dolan, Goddard, and Montague. And so with the student Ranveer Singh, we've indeed realized the supercurrent in the way Jeff and I envisioned. So here's the OPE of two of these vertex operators of dimension 3/2 associated with spinors, vectors in the era of the Heisenberg group of translations. And the bad term here is this one right here, which is associated with these vertex operators, EDI lambda x, where lambda squared is 4. What's K of lambda? That's what Jeff and I didn't know. So K of lambda turns out to be very simple. It's just the action of the translation by the half lattice vector on the state psi inner product with psi. So once you realize that, the rest is relatively clear sailing. You construct a maximal abelian subgroup in the Heisenberg group, and you sum these translation operators over that maximal abelian subgroup, and check that again it's a rank 1 projection operator. So how do we construct the suitable maximal abelian subgroup? We can do that if we can find a sublattice of the Leech lattice. I'll call it the superconformal sublattice with the following properties. The inner products of any two vectors is even. It contains twice the Leech lattice with index 2 to the 12th. It's contained in the Leech lattice with index 2 to the 12th. All the vectors have norm square 0 mod 4, and the non-zero, the minimum non-zero vector norm squared is bigger than 4. So if you have such a sublattice, then you can choose an isomorphism of T2 of lambda with F2 to the 24, and this Lagrangian subspace becomes a code subspace. And then the claim is the supercurrent is a current for a vector psi in that one-dimensional space. And then the argument that it is a supercurrent is very much analogous to what I did with Jeff. So if lambda squared is equal to 4, those are the bad terms, then this T of lambda takes you out of the code space into an orthogonal space. And so that inner product is 0, and because of the error correcting properties of C, and so we get a superconformal current in the B&B formulation of the monster. So we need a sublattice that does this. Now there's a very beautiful paper by Dong, Lee, Mason, and Norton where they point out, among many other things, that there's an isometric embedding of L scaled by the square root of 2 into the Leech lattice for every Niemeyer lattice L, and if we take the Leech lattice itself, that does the job. Now, are there others? Well, I don't know. There might be other sublattices with those defining properties, and so it's possible that the B&B model actually has several supersymmetries. I don't know. We're looking into that right now.
So this doesn't work for any of the Niemeyer lattices with roots because then you have length scored 4.
Yeah, exactly.
The minimum length has to be.
Yeah, you need that for the error correcting code to work.
So the minimum length can be 8 because it has to be 0 mod 4.
That's right. It could be 8, yeah. Or it could be bigger.
Yeah.
It just has to be bigger than 4, so that when you act with the bad term is from T of lambda with lambda squared equals 4, and you want to take that out of the code subspace.
So if I take 2 square root of 2 Leech lattice, does that also work?
No, I think not, because you see, we also need this property. We need this to be, that'll be too small.
I see.
All right, so time is running short, so I better start running. So I thought I would talk about time reversal in abelian term-Simon's theory. And one of the justifications for that is that several of my recent works with Jeff have involved discriminant forms of lattices in various ways. So here's another application of finite abelian groups equipped with a quadratic form. Excuse me, I misspoke. Not a quadratic form, a quadratic function. So a quadratic function on a finite abelian group, D, is a function from D into R mod Z, so that if I take Q of X plus Y minus Q of X minus Q of Y plus Q of 0, then that is a bilinear form in both X, so it's linear in both X and Y. That's the quadratic function. Now, the physics question here is, when does three-dimensional Chern-Simons theory have a time reversal symmetry? So usually people write that when they talk about Chern-Simons theory, and doesn't look very promising for time reversal, but we need to remember that the general theory is based on a compact group G and what's called a level. And so the right question is, which compact groups G and levels give time reversal invariant theories? And there are indeed some non-trivial examples of time-invariant Chern-Simons-Witten theories, which appeared in a paper of Cordova, Shin, and Zyberg, and also in previous papers by Nati and other collaborators. As far as I understand, there's no systematic understanding of when this can happen. So with my student Roman Gecko, we've recently carried out a systematic study, but for the limited class of spin Chern-Simons theories with a torus gauge group, namely a product of U1s. And anyone who's thought about the quantum Hall effect, fractional quantum Hall effect, knows the Lagrangian for this is given by a K matrix with a bunch of U1 gauge fields. So Kij is an R by R non-degenerate integral symmetric matrix determining an integral lattice lambda. And the classical time reversal invariance means that there's a way of redefining my gauge fields by a U, which is in GLRZ, such that K gets conjugated to minus K. Notice that that is only possible when the signature is 0. But there can be quantum time reversal symmetries which are not visible classically. And both of these points were explored in a paper by Del Mastro and Gomez, but for the rank 2 case, and I actually scooped my work with Roman. But Roman and I decided there was more to understand, and I believe that we have found that there is more to understand. Now, why can there be quantum time reversal symmetries which are not visible classically? Because the quantum theory does not depend on all the details of the lattice L. So what does it depend on? Well, it certainly depends on the finite abelian group called the discriminant group by mathematicians, L dual mod L. And in physics, that's the group of abelian anyons, or also known as the group of one-form symmetries. And the quadratic function is physically the spin of the anyons, and it's given by this formula here, where capital W is a characteristic vector on the lattice. And that quadratic function satisfies this interesting identity that this Gauss sum is given by e to the 2 pi I times the signature over 8. So the basic theorem here is that the quantum theory only depends on the triple of this finite abelian group, the quadratic function, and sigma bar, which is an integer mod 24, where q and sigma bar are linked by the Gauss sum is this phase. And conversely, every such triple arises from some torus Chern-Simons-Witten theory. Now, I should say what I mean by equivalence class. So we could say that two triples are equivalent if there is an isomorphism from d to d prime and a shift vector delta prime so that the quadratic functions are related in this way. Okay, so now I've almost given you the problem I need. We need to say what is the time reversal criterion. So the time reversal criterion is that the d, q, and sigma bar is equivalent to d minus q minus sigma bar. Now, why q to minus q? Because q determines the spin of the anyons, and spin changes sign under time reversal. Or, if you prefer, q determines b. B is the braiding of the anyons. If I have anyons and I braid them this way, and then I time reverse the process, it goes this way, so it's the opposite braiding. So if I have abelian anyons, of course, the phase has to get complex conjugated. So b has to go to minus b. All right, so now I've got a well-defined problem. Classify finite abelian groups and quadratic functions such that this equivalence relation holds. That's a hard problem. Fortunately, a simpler version of that problem has been known in mathematics going back to the mid-30s. So remember that b is determined by q, by this formula here. So let's throw away q and sigma bar and just keep b. And let's try and classify finite abelian groups with bilinear forms. That's called the Witt group. So you start out by realizing that there's a natural way of adding equivalence classes of abelian groups with bilinear forms. And this forms what's called an abelian monoid. And then there's a sub-monoid of so-called split forms where the abelian group is a sum of d1 and d2, where b restricted to d1 is 0 and d1 is its orthogonal complement. So the mathematical term is that d1 is both isotropic and coisotropic. Those are the split forms. And now if you mod out by those split forms, you get an abelian group. And it's an abelian group whose structure is known. If I had more time, I would explain it. But roughly speaking, it's an infinite number of copies of Z2 and an infinite number of copies of Z4. Now we're interested in the submonoid of forms which are equivalent to b goes to minus b. And we, that is Roman, computed the generators for this abelian subgroup and then refined it to T invariant triples. And the theorem is that a T invariant triple must be a direct sum of a very definite list of examples. So here's a very definite list of examples of finite abelian groups with quadratic functions. And as an example of a theory with a non-trivial time reversal invariance that's not there classically, you could just take the A4 lattice or the D4 lattice. They can be primitively embedded into E8. And so that automatically gives you a lot of things that lets you to check that they're quantum T invariant, but clearly they're positive definite lattices, so they can't be time reversal invariant. You need a signature 0. So the conjecture for the general case is that if I have a group G and a level K, then I get a Chern-Simons-Witten theory. And famously, the Chern-Simons-Witten theory leads to what's called a modular tensor category. And the mathematicians have defined a mathematical notion of a Witt group of braided fusion categories. Modular tensor categories are examples of braided fusion categories, so our conjecture is that the Chern-Simons-Witten theory is time reversal invariant if and only if its class, its modular tensor category, is order 2 in the Witt group. We don't know. We've been trying to check some of these non-abelian examples that Nadia et al. I got 5 minutes, so it's time for a raucous, quick jig. What?
Which of these theories are spin theories and which are bosonic?
Well, in I don't know for general K and G, but for the abelian case, it's when there's an odd, when the lattice is even and odd. So the spin theories are where the lattice L is an even lattice.
But then they're time reversal
Excuse me,
invariant on
the
the
non-spin theories are when the lattice is an even lattice. If the lattice is not even, then it's a spin theory.
So for example, U1 level 2 is usually considered to be time reversal invariant, but it's
only
time
as a
reversal
spin
invariant as a spin theory. It's not time reversal invariant as a non-spin.
Okay, we need to talk about this then. Okay, I got 5 minutes, and that's going to take more than 5 minutes. Okay. All right, so a quick jig. So I'm going to talk about actually 2 new directions in the relation of super-Yang-Mills and 4-manifold invariance. And Jeff hasn't worked on that recently, but I think it was at least once upon a time an interest of Jeff's. He wrote a very curious paper with Andy where they interpreted the Donaldson polynomial as a scattering matrix of axions off 5 branes in heterotic string theory. The first of these 2 projects is generalizing Donaldson invariance to families of 4 manifolds. So this is a project with Jay Cushing, who is an undergraduate here at Chicago, and Martin Rocek, whom I think you all know, and Martin's student, Vivek Saxena, who is now an excellent postdoc at Rutgers. So let me remind you that if we have a twisted vector multiplet in 4-dimensional n equals 2 super-Yang-Mills theory on a 4-manifold X, then we can look at its partition function. And a priori, that metric, the action, to write the action, I need to use a metric. So a priori, the partition function depends on the metric, but Witten pointed out that because of this topological twisting, it's actually a constant function on the space of metrics. That's how I want you to think about it. And so therefore, it's a smooth invariant of 4 manifolds. Those terms are the same as constant on the space of metrics. So what we did is we coupled to a twisted and truncated version of conformal supergravity. This is very, very technical and very, very complicated. But to simplify things quite a lot, what we're doing is we're introducing a fermionic partner, psi mu nu, which is a symmetric tensor, a partner to G mu nu. So we're coupling the background fields of bosonic G mu nu and a fermionic psi mu nu such that there's Q symmetry, where Q relates G mu nu to psi mu nu. And mathematically, psi mu nu is just a cotangent vector on space of all metrics. And then the output of a lot of work is that it defines a closed differential form on the space of metrics mod diffeomorphisms, and which is also known as B-diff. And therefore, the cohomology class of this form should be a smooth 4-manifold invariant And we've had enough trouble just formulating the theory that we don't know much about the path integrals. So the question that remains is whether these actually define new and interesting invariants or not. We don't know. Let me say a few more details here to try and do a little bit of justice to it. So in the twisted vector multiplet, we have a Q symmetry that relates A mu to a twisted gaugino, psi mu, and psi mu to D mu of phi. Phi is the adjoint scalar in the vector multiplet. When we couple to background gravity, we have to introduce G and psi, and for technical reasons, a vector field, capital phi mu. And when we do that, we have to modify the Q symmetry action. So the action then, to write the first term in the action is easy. It's got to be the twisted gravitino times lambda, where lambda, Q on lambda is T mu nu. But the dot dot dots is no easy task, and as a result of heroic computations by Jay and Vivek, we have the whole story. And one of the interesting conceptual points that comes out of this is that it's hard to write observables when you include background gravity. In Witten's case, he observed this famous descent operation that allowed him to write Q invariant extended operators. But when you couple to gravity, you get an extra term that looks like that, and that spoils the whole story. So it's actually quite hard to write observables, so that nevertheless, the partition function itself is very interesting. Okay, last thing, will take about 3 or 4 minutes, you can also go up to 5-dimensional super Yang-Mills, and this is a collaboration with Jan Mansgaard in Dublin and Shenyu Zhang, a postdoc at Daisy, Hyun Kim, who's an assistant professor at Rutgers, and her student, Runkai Tao. So you can take 5-dimensional super Yang-Mills theory and put it on a 4-manifold times S1 and then twist so that at least it's topological in the 4-manifold directions, although not on the S1 direction. Indeed, if you reduce on the X4, on the X, on the 4 dimensions, you get a super quantum mechanics whose target space is the moduli space of instantiles. So if we introduce a dimensionless radius, which is the radius R of S1 times the 4-dimensional scale, then the partition function is a series in R where, because we're studying super quantum mechanics, what do you do with super quantum mechanics? You calculate the index of the Dirac operator, and by the Atiyah-Singer index theorem, that's the integral of the A-hat genus. So that's the kind of thing you're expecting, and that goes back to observations of Nekrasov in the mid-90s. Now there's an interesting story, including observables. In 5 dimensions, we have a U1 instanton symmetry with a current, where I'm using Zyberg's notation here. The capital A is for the background fields, small f is for the dynamical non-abelian gauge field. So there's a 4-form conserved current, and we can couple it to a background gauge field A. The background gauge field A can have a non-trivial topological class, N. And so we can form new observables, that not there in Donaldson theory, where we have a mixed Chern-Simons term, or if you prefer, Chern-Simons term over 3-manifold sigma times S1, where sigma is point create dual to N. So now we have a partition function, which is a function of R and N. And now using 2 techniques, 2 totally different techniques, but getting the same answers, we've used both the Coulomb branch integral, namely the U-plane integral, and independently localization techniques, and we reproduce and extend some beautiful work of Gocha, Nakajima, Yoshioka from 16 years ago, and some more recent work of Gocha, Martin, Kuhl, and Williams. And so here's an example of the partition function for 4 manifolds with B2 plus bigger than 1. And a lot like Witten's master formula for the 4-dimensional case, it's a sum over spin C classes weighted by the Zyberg-Witten invariant. Some very definite function of R raised to powers that depend on this topological class N of the background gauge field. So that concludes the Jig with a big rush, very, very fast. And happy birthday, John.
Okay, thanks, Greg, for the beautiful partita questions.
So I have not followed all the developments in Chern-Simons theory. This might be a very naive question, but is the condition that you found for quantum time reversal symmetry, does it have a nice interpretation if you consider the Chern-Simons theory on a three-manifold with boundary and ask whether it reflected in the property of the edge modes?
Yeah, that's a good question. I thought a little bit about that. That's a confusing question because if the lattice is positive definite, you'd think that they'd all be left movers. How good left
How could it
movers?
be time reversal?
Time reversal invariant, yeah. So, the strict answer is we're restricting ourselves to the topological theory. Now, it does extend to the fully extended theory. So if you had topological boundary conditions, and you go down all the way down to a point, then so Gelov and I claimed only the top two cases, three-dimensional and partition functions in Hilbert spaces. Say we claim that those are determined by D, Q, and sigma. And then Dan Fried and Jacob Lurie and Konstantin Telemann and Mike Hopkins then extended that statement to the fully extended theory. So that does include things like topological boundary conditions. And they do claim that, again, that the theory is completely determined by that triple. But if I take other boundary conditions where I have modes with energy and so on, I don't see this time reversal statement.
So it's purely something.
So this is about the
property of
topological theory, yeah. For this very simple reason that if they're all left movers, how could it be time reversal invariant?
I'm sorry.
But does it imply
is
some other symmetry, or this is just not time reversal?
No, this is not clear to me at all. The example I know
Yeah.
is both left movers and right movers.
Sure.
So it's not purely left movers.
No, but I'm saying if you have a positive definite lattice, then they're all going to be left movers.
But then it's not, but then I don't think it would be time reversal invariant.
Well,
The
that's
example
my
I-
point, that you can make theories where the topological theory is in fact time reversal.
But C
What's the
changes,
definition of
C
time
changes.
reversal?
C
invariant?
No, C
Right.
changes
C-
sign. The framing anomaly changes sign.
No, it's sigma bar mod 24.
So
So sigma bar
What's
is
sigma?
going to minus sigma bar.
yeah.
So sigma bar could be 0 or 12.
So all your models have sigma
So
is the
we
framing
have to
anomaly?
choose, so that was a mistake in the draft, which I pointed out to Roman, but we haven't had a chance to fix the draft. So you saw sigma mod 8 on the draft. It has to be sigma mod
So the
4 is
canonical
0.
example is U1 level 2.
Well, that's not gonna have sigma 0.
That's right, but it is time reversal invariant.
You and I have to debate what we mean by time reversal invariant, because there's a framing anomaly and that complex conjugates.
Right, so the answer there is that it's U1 level 2 times U1 level minus 1. That's the proper way to state it. And then the framing anomaly vanishes.
Okay, but then there's gonna be a K matrix, which I'm gonna claim satisfies our criterion. And so we'll
Yes.
compare. Yeah, okay,
But then,
but then there's no contradiction.
No, but then you don't have left movers, this issue with left movers and right movers.
Oh, sure, in that particular, for that K matrix, you're gonna have left movers and right movers. What I'm saying is you can have a theory where if you put non-topological boundary conditions, you could in principle just have left movers. And that would obviously not be time reversal invariant, so I'm only making a statement about the topological theory. So I think what I'm saying is consistent with what you're saying.
So your construction of your lattice construction of the supercurrent.
Yeah.
Was so obviously beautiful, what could possibly be the problem with it?
Well, I'm sure there are two problems. And as I said, I generated a lot of long emails from Theo, which I have not had time to parse. And Theo is a very deep thinker in this area, so I just need to see what he has to say. But I got really worried that he's explaining to us that we're all wrong, and I did scan through it to make sure he isn't saying
I
that.
mean, I thought Jeff said there was a problem with it.
Is there a name for the code that you had to use?
No, I'm not.
So it's not a known code.
I've never seen anything like this. I
You
mean, I
look in the
didn't.
code
I didn't know
tables to see
about
if it
this
was
Don Lee Norton paper theorem.
But there are tables of known codes. It's not one of the.
Have not checked. And there's a whole issue of, there's no canonical isomorphism of lambda mod 2 lambda with F2 to the 24, right? I mean, if I have, codes are going to be expressed, your tables of codes most likely are going to be expressed in here, but I can compose any isomorphism with an automorphism of here. So I don't know. We certainly haven't done that.
Greg, you said that the time reversal invariant Chern-Simons theories are all Z2 classes in the Wick group?
Our conjecture, and this is very much a conjecture. Now, Roman has been checking this, and it's non-trivial. It involves these higher central charges, so which are homomorphisms from the Witt group into into U1. Let me be just safe and put it into U1. So Roman has been checking that, and so he tells me that it works for the examples in the Kordevish and Zyberg paper.
But so do you know this classification for the abelian Chern-Simons, for example?
We gave the classification. That's
right.
Yeah, that's a non-trivial thing that Roman did.
Oh, for sure.
This list here, everything is a direct sum of these. We have to correct the sigma mod 8 to the sigma equals 0. So we want sigma mod 24 to be 0.
Right.
This needs to be changed, and it will be.
Sure. I guess my real question though is, are there any Z2 classes for abelian Chern-Simons that are not time reversal invariant, or is it a one-to-one statement?
Our conjecture is that it's necessary and sufficient.
So in your classification of the Wick group, you had a Z2 and you had a Z4. Do you know?
Well. The old Witt group due to Witt is an infinite number of Z2s and Z4s.
Yeah.
And so
This is great.
yeah, I see. I think I understand. You want to look at the subgroup of the Ostrich et al. Witt group of modular tensor of braided fusion categories that comes from the abelian cases, and ask, is that group known? And is it if and only if it's order 2 and I can.
Yeah.
Excellent question. I don't know the answer to it.
Okay.
One last quick question.
I was just going to ask if there's a way to run your machinery backwards to go from these sub-lattices to produce error correcting codes.
Yeah, this was brilliant.
Yeah, right. So you see, if you have a sublattice, then you have lambda superconformal mod 2 lambda, which is sitting inside here. Choose an isomorphism. That gives you the error correcting code in here.
All right, I think we should move on. So let's thank Greg again.